This 4.56 kilometer bridge is Indian Railways' longest truss bridge. The foundation laying had already begun in 2002. It was decided by the ministry to add a roadway above the railway track. By that time, the foundation and the substructure were already complete. Fabrication with 2.5-inch steel plate was itself a task. Special radial drills and guide jigs become essential when numerous identical drill holes are needed in large numbers. The drill needs to be precise and absolutely correct in position. Once drilled, these plates will become part of a bigger steel component of the bridge superstructure. Then, these plates are welded to form a member of the steel truss. A special welding technique, submerged arc welding, is being implemented. It involves formation of an arc between continuously fed bare wire electrode and the workpiece. The process uses a flux to generate protective gases and to add alloying elements to the weld pool. When molten, the flux becomes conductive and provides a current path between the electrode and the workpiece. The molten weld and the arc zone are submerged under a granular fusible flux consisting of lime, silica, manganese oxide, calcium fluoride, and other compounds. This prevents any atmospheric contamination. Since the operator cannot observe the weld pool, great reliance must be placed on parameter setting and positioning of the filler wire. As the arc is completely covered by the flux layer, heat loss is low. There is no visible arc light, the welding is spatter-free, and there is no need for fume extraction. Once the steel is welded, it is thoroughly checked for perfection by dye-penetrating testing. Here the white color shows the weld is seamless. steel components are then sandblasted and metallized. Sandblasting involves propelling very fine bits of sand at high velocity to clean the steel surface. Once sandblasted, the steel is metallized with a coat of aluminium. This will provide environment and corrosion protection to the steel for decades. The erection of superstructure started in September 2010. The steel truss cantilever bridge was a major engineering breakthrough when first put into practice. It can span distances over 460 meters and can be more efficiently constructed at difficult locations by virtue of using little or no structural reinforcements. The construction begins with one span on ground. This serves as the anchor span for cantilever cranes mounted on top of the steel superstructure. Supported by a link member which holds the free end, these cranes build the next span member by member, launching ahead without any other propping from the ground. The cranes move on top along the truss structure, adding one member at a time, forming an entire span from the free end, and land on the next pier. Before cantilever launching of a new span, the bottom chord of the new span is blocked for any backward horizontal movement. It is done by inserting a buffer block between the bottom chord of the anchor span and the bottom chord of the new span. The vertical movement of the buffer block is monitored to assess the vertical deflection caused at the far end of the new span being launched. For cantilever launching, the fabricated members were lifted to the rail level by ground cranes, then transported on temporary tracks. At the launch end, these members were lifted by cantilever cranes and fixed with drifts and bolts. On one single span of the superstructure, there are over 100,000 rivets. Rivet is a permanent mechanical fastener. It is a smooth cylindrical iron shaft with a head on one end. The end opposite to the head is called the tail. It is heated and immediately placed in a drilled hole. And the red hot tail is then pounded to form a new head. In other words, pounding creates a new head on the other end, resulting in a rivet that once cooled has fixed itself permanently on both ends. These rivets hold the steel components fastened together permanently. And if the alignment of the truss does not match the central alignment of the bridge, the entire 2,240 metric ton truss will have to be shifted into alignment. To build a road deck on the second level of the steel structure, the engineers had an unprecedented challenge. The concrete casting could have been done by providing traditional support reinforcements from the rail level below. But the engineers had to find a way that would not hinder the railway work and accomplish both tasks simultaneously without affecting the other. So they developed a gantry that runs on the rails and holds aloft a large steel shutter that provides the support needed for the road construction above. On the deck, the shutter is fixed and team is welding shear studs into the steel structure. These shear studs prevent the slip between concrete and steel structure and help achieve a much stronger bond. Shear studs transfer and balance the stress between steel and concrete in a composite structure. Stud location and straightness of alignment of row over the steel cross girder and road stringers is marked with precision and care. Surface around welding location is cleaned by buffing wheel and made free from rust, dust and paint. The stud welding gun uses a type of flux called ferrule, a ceramic ring, which concentrates the heat, prevents oxidation and retains the molten metal in the weld zone. The ring is then broken and removed. An expansion joint is an assembly designed to safely absorb the heat-induced expansion and contraction of construction materials. It absorbs vibrations, it holds parts together and allows movement due to down settlement or earthquakes. This joint greatly reduces the stress that would otherwise be caused to the main structure. The first anchor span was erected on trestles in September 2010, initiating cantilever erection from the southern end. While on the north side, the erection began in January 2011. Taking advantage of the dry weather, additional anchor spans were built wherever there was ground support. Even midstream, the span number 27 had a patch of land underneath, adding a third front for the cantilever erection. But in 2013 floods, the land got washed away, so a floating barge was used to feed the material for midstream cantilever erection. This expedited the progress, and within 4.5 years, the erection of superstructure was complete. On 2nd of January 2015, when a bottom chord member was placed to bridge the last gap, the link between north and south was finally established. August 2015, the air resounds with victorious and joyous cheers of people around. The engineers are ready to run their first railway engine over the bridge. Connectivity is the key to economic prosperity. When human resource is mobilized, unprecedented growth can be actualized. Job opportunities, agricultural exchange, tourism, increased productivity and efficiency are some of the immediate gains the bridge will deliver. However, homogeneous growth, decongestion of urban areas, and increased participation of villages to Bihar's economic growth will be the key long-term impact of this initiative. Bihar stands on a threshold of a dynamic phase for growth and development. This bridge over Ganges, connecting Patna with Sonepur, will be a turning point for Bihar.